Hey everyone, Mrs. Basega here, and today we're working on the Magnetism Review Guide, erroneously labeled Unit 9. It's really Unit 8. Anyways, just like last month, the way that this review packet works is this one section on permanent magnets corresponds to the first page. Everything on the first page of this review packet corresponds to these objectives. So when you get through the first page, make sure you can check off and explain how alignment creates magnetic poles. Describe why magnets are dipoles, right? Describe the force interaction between magnetic poles. You can do all this. So let's get to it. I suppose before we get to page 1 though, this page is super useful because it has all the equations for this unit and all 3 right-hand rules you'll be responsible for. Just so you have a little note off the top of your head here, be able to do proportions with these 2, be able to do calculations with this force equation, be able to do calculations with Faraday's law, the one where the changing flux creates a voltage inside a coil, and be able to do it with the shortcut equation, Faraday's law when an object is either entering or exiting a field. You should do all 3 of these right-hand rules with pictures that go along with them. So let's get started. The north pole of this magnet is located at D. That's because this picture shows domains, and domains point towards north poles on the inside of magnets. On the outside of magnets, there are magnetic fields that point away from north and towards south. A compass would point in the direction of a magnetic field, so compasses actually point south. This permanent magnet can be made of any material except copper. This is because copper has paired electrons. If you were to look at its electron diagram, all of its electrons are paired up, so there's no net spin. You do need to know that too. Both iron, nickel, and cobalt are materials where there are unpaired spins. Iron can have up to 5 spins all going the same direction, so it has a net magnetic field. Now, iron can be a magnetic material. It has domains. But if I just take a regular piece of unaligned iron, it doesn't pick up other things. That's because the iron skillet's domains are not aligned yet. Right? So if I took, a house key, a spoon, a fork, I can't just take those and bring them near paper clips and expect them to go pick each other up. When I take a spoon out of the drawer, the spoons don't attract each other. That's because you need at least one material with aligned domains in order to have attraction. Now, let's say I had some troublesome high school students in class and they decide they're gonna throw some magnets around the room and my magnet gets broken in half, right? You know this. The domains are gonna stay aligned. They continue to point towards north and away from south. But if I were to cut this magnet in half, like here, well, the piece on the right would have a south pole, domains point away from the south. The piece on the left would still have a north pole, so you'd get 2 magnets. Because the domains are still lined up, they have the same strength as the original unbroken magnet. So, is 1/2 still as strong as the original? Yes, because the domains are still aligned. Now, before, we had the domains pointing on the inside of this magnet, pointing towards the North Pole. So let's draw our domains first before we draw the field lines. They point towards north on the inside. Those are your domains. Getting a little lazy there. The field, however, points away from north and towards south. Now, when this happens, notice that it forms complete closed loops. If I were to follow this away from north, and assume I drew my arrow correctly, away from north towards south, I would see this circle being formed by the magnetic field. Same thing over here. This goes away from north towards south. The fields and domains line up to form a circle, or something like it. On this next one, the north and south poles can be determined because I see where the field lines are. It points away from north towards south. So I've got my labeled poles, and the place where the field is strongest would be the place where the lines are closest together. B has field lines that are very dense, so B has more field. Then let's see, C looks like it has the field lines are closer together. Then D, then A. Don't worry yourself too much if you switched C and D. Those are kind of similar to each other, but definitely note B is the most, A is the least. So keep in mind that you want to check this page against this set of objectives to make sure you've learned all the things you need to know. So we talked about alignments of domains. We talked about how they're dipoles. When you cut a magnet in half, it makes two separate magnets because each magnet is a dipole with one north and one south pole. We know the force interaction is like the opposites attract bit. So these two would attract each other because south attracts north. We can draw fields, we did that. We talked about ferromagnetic materials having many unpaired electrons, whereas non-magnetic materials like copper have all their electrons paired up. The one thing we didn't test on here was use a compass to determine poles of magnetic field, but you should know a compass points towards north. So knowing this compass direction would mean I know that I said it funny. Compasses point south from north to south. So knowing this compass direction, we'd be able to identify that A is a south pole. See, I did it right. All right, second objectives, magnetic fields. Magnetic field for a single wire forms a circle. You should know that this X symbol means into the page. And using the right-hand rule, I'm going to put my thumb into the page. This leaves my fingers curling in the clockwise direction. So I would draw the magnetic fields in circles. You should know that the magnetic field around a current-carrying wire is a circle. In this case, the current is traveling into the page. That's what that X stands for, and yes, you must know that. No, that's not on the equation sheet. The magnetic field is going clockwise. And when I'm thinking of like points near this wire, points that are close to this wire have strong field. Points that are far from this wire have weak field. Now let's say I take the same exact diagram, okay? So picture I'm putting my thumb into the page, I've got this clockwise curl. What if I rotate it so my thumb points to the right? Just like in this diagram right here. If my thumb points in the direction of current and my fingers are going, well, in this clockwise direction, that means the field is going out of the page at point P, so I'm going to draw some dots. And into the page below the wire. Into and out of the page are opposite directions of each other. So if you know there's into the page field on top, there must be out of the page field on the bottom, and vice versa. Because of the circular nature, any 2 points on opposite sides, let's say this point here and this point here, any 2 points on opposite sides of the wire from each other have opposite direction field. Now, if you're having trouble picturing like Y dots and X's, you can do this trick. You can draw your right hand And note that wherever your knuckles are the dots, and wherever your palm is the X's. You could write that on your hand, but I'm not going to do that. I would not be offended if you did. But you have to know that current points with your thumb and leaving your fingers for field. You need to know it's a circle. So the next ones are all what happens if. So I drew my magnetic field. What happens if I reverse the direction of current? Cool. Well, it would have the same size strength at point P. So B would be the same size field, but it would switch directions. Because imagine I'm taking my right-hand rule here and pointing it in the opposite direction. Now it'd be going into the page on the top and out of the page on the bottom. Next, point P is moved twice as far away. According to this equation, we have an inverse relationship between R and B. So if R increases, that's the radial distance to point P, then the field gets weaker. That's what I was trying to illustrate up here. The farther you are from the wire, the weaker the field. So if it's twice as much distance, it would have half the field. That's a straight up just regular inverse relationship. It's not an inverse square where it would be a quarter of the field, as if we were talking about gravity or electricity. Magnetism is a regular inverse. So remember, you can ignore this 2 pi, you can ignore the mu, just use this inverse relationship. A farther distance means less field. Now, if it were the same distance away but below the wire, it would have the same size field but in the opposite direction. So same magnitude is, think size, same magnitude of field, but opposite direction. Finally, if the current triples, then this same equation shows that the field would also triple. 3 times I would mean 3 times field. It's a direct relationship because I is in the numerator of that equation. So let's check. Did we draw and describe the magnetic field around a straight wire? Yes, it's a circle. We drew them. We did right-hand rule. We described that it has a straight wire relationship that has current increasing to make a increasing field, and increasing distance means less field. We talked about how you don't really need the 2 pi and the mu out here because we're not calculating them, but be able to know those things. So then, electromagnets. With the electromagnet, we need to know the direction of conventional current. Conventional current goes away from positive and towards negative. So if we looked at our currents right here, this must mean that I have a negative side over here and a positive side over here, because conventional current points from positive to negative. Once I know the direction of conventional current, wrap your fingers around an object so that your fingers point like this. That might look like this. Not super comfy. We'll live. In either case, my thumb points to the left, making that a North Pole. So the South Pole must be located at B. This is an electromagnet. Whenever the current is on, it forces the domains of this iron rod into alignment. Whenever the current is off, the domains go back to their merry business of being unaligned. Now, use the same rule 2 more times. First, I'm going to wrap my hand around to make this. So to make my fingers go down in front of this, I'm wrapping my fingers in the direction of current. My thumb points north. If I reverse the direction of current, I must reverse the polarity over here, so my thumb would point left. Fun fact, if you ever change the direction of current, it always makes the field switch directions. That's true for both single wires and electromagnets. Well, now that I know this, I see these repel each other because opposites repel. That's what we're talking about here with the force interaction between magnetic poles. We know that opposites attract, likes repel. Now, this has a field equation. B is equal to mu Ni over L. Using proportions here, if you put in 4N and cut the current in half, so that's 1/2 I, then this would be 4 divided by 2, it would be 2 times more field. Even though more coils means more field, well, if there's less current, there's less field, and those partially cancel each other. To make a good electromagnet, you need something with a strong permeability. Now, depending on how you measure permeability, its units are kind of funny, so we're not going to deal with them. But know that the bigger the number, the better the core material. So the student claims that replacing iron with nickel will be more effective. I would respond that they're wrong, because replacing iron with nickel would mean that you would have fewer domains. Permeability tells you how easily the magnetic field travels through this material. Iron is the better material because it has the better permeability. It would make a stronger electromagnet. Another student says, well, couldn't you just use copper? They're both metals. Okay, they are both metals, but as we said on page 1, copper is not a magnetic material. Its electrons are all paired up, so they don't make their own little mini magnets. Copper atoms are non-magnetic. You could put copper in the core, like you physically could, but it wouldn't be a good choice because it doesn't have domains. Without the domains to pop into alignment whenever the current is turned on, you'd only be left with the field of the solenoid, and that in itself is relatively weak. The core seriously increases the amount of field an electromagnet can produce. So, this equation, as you saw, proportions only. I call this the 4 C's. You should know that for a solenoid or coil, you can call it either one. For a solenoid, the field depends on the core, current, number of coils, and compression. Compression, you want those little coils close together, because if they're close together, the field is compacted and stronger. We use the right-hand rule to get where the north and south are. We talked about why a ferromagnetic core is better. We talked about the direct relationship with current, coils, and core, and the inverse relationship between the length of that coil. Geomagnetism. Now, this one actually has more standards than I put on this list, right? So let's talk about those. You should know what the seafloor spreading picture looks like. What this picture means is as a magma comes up between these two plates, it hardens. And as it passes the Curie temperature, the domains go from shaking around irregularly to settling. And they all settle to have your domains point towards wherever magnetic north was on the time that this rock cooled. So it's kind of like having a fossil record of where was the North Pole when. Now, in this case, it says the strips alternate direction, with the gray regions having a magnetic field in one direction and the white region having a magnetic field in the opposite direction. Currently, the magnetic pole near the north geographic pole is it's not positive and negative, I'll tell you what. This is actually asking about the current Earth, which is kind of confusing because the picture right above it is looking at seafloor spreading, but this question is actually asking you about the Earth. Now, we call this quote unquote north. Up there with like Santa and polar bears in the Arctic Ocean, right? It's called a north, but it's really a south pole. I probably won't ask you a question like that as a straight up just factual know it question, but so you know. This pole is a true magnetic south. Like I told you in class, and I'll tell you again, the reason those names are backwards is that early explorers were looking at their compasses and they're like, oh, yeah, my compass, it points over here. The north pole of my compass points up there. Let's call it north because that's where the North Pole points, guys. But that North Pole is attracted to south. That's why their compasses were pointing in that direction. The compass points away from north, and they were mistakenly thinking that the north points north. No, norths are attracted to south. That's what's up. So if this were the Earth, and sorry my drawing's a little bit bad, what we call the north in the Arctic Ocean up above Canada is a magnetic south pole. Now, let's say that's currently where the south is, and let's say this is current times, and we'll put south over here, all right? Domains are pointing north. Most current strips are going to be nearest where the magma is coming out. So imagine the magma comes out right here and it solidifies in place. A is the youngest strip. E is the oldest. They alternate directions because this north and south pole thing, it isn't permanent. They change over time. They change over time because the Earth has a special layer. Yes, its core is made of iron. That's not why it's magnetic. It has a special layer called the outer core, and the outer core is liquid. We can actually prove this with earthquakes, and we'll talk about that next unit. The outer core of the Earth has this little dynamo. It has these currents of molten iron, and the currents of molten iron create this changing, moving north and south pole. We watched in class how it changes even in, a few human lifetimes. The reason that the fields switch direction is because the dynamos randomly move. Right? And as rocks come out of this opening in the mid-oceanic ridge, the domains cool, giving you a geographic record of where was the North Pole. So the strips alternate because as the domains cool down, they align themselves towards magnetic north. Remember, domains point north. They align themselves pointing towards magnetic north so that as the poles change inside the planet, the rocks give a fossil record of that. Now, this proves that Earth's tectonic plates, right, move. What other evidence is there? We have old-timey plant fossils, old-timey animal fossils. Hominids are us, guys. We weren't around back then. I want you to think human language is only about 10,000 years old. We certainly didn't have hominids millions of years ago. So no, not hominids. We certainly didn't have human language back then. But we can prove Earth's tectonic plates moved because of plant fossils, animal fossils, mountains that match up, the magnetic strips, right? We can see that the Earth's magnetic field changes over time. All of those are evidence that Earth's tectonic plates are the correct theory of how our continents on our planet work. Now, we like having this magnetic field. Right. We like having this magnetic field on Earth because it protects us. So I want you to imagine that this is a person standing on the surface of the Earth, wanting to not be irradiated. When light leaves the sun, right, the sun actually puts out more than just light. It puts out highly energetic particles. So I want you to imagine an electron, but moving 450,000 miles an hour, right? That's a lot of kinetic energy. And when that particle hits you, it kills the cell that it hits. Now, as humans, we have lots of cells. It's okay if we lose a few of them. But if you're talking about early life forms that are single-celled organisms, well, that could kill all the single-celled organisms they came in contact with. That would seriously prevent evolution of life beyond the stage of, single cells. That'd be a problem. So Earth's magnetic field is important because, one, where does it come from? This little liquid layer. And two, it protects life on Earth, right? By deflecting the fast-moving solar wind particles away from the parts where humans are currently living and towards the poles. Towards the poles is really cold. There's not a lot of life up there. So it had minimal impact on their evolution. Right? So it lists on here only the magnetic field, the cause and importance. I would say that's probably the most important one, but I went over lots of things on that page. So double check the answer key. 5. Magnetic force on a current carrying wire. This is where we start to get, instead of the thumbs up right hand rule, the high five right hand rule, right? How to do this rule. We want to take our single thumb, you have one thumb, and point it into the direction of current. And I know that sounds funny. The reason I say this is I have more fingers than thumbs, and you will always be drawing multiple field lines, right? Field always is going to have multiple lines, whether those are into the page dots, lines to the right. Field will always have more field lines than current will. So what I need to do is match my thumb to the upward direction where I is, thumb up. Fingers are pointing to the right. Imagine my palm is pushing this wire into the page. I know that it has to either be into or out of the page. Into the page is the palm away from you. If it were out of the page, my palm would be up, facing me. In fact, you could have just narrowed it down to two of them. Since B is to the right, the magnetic force can be neither right nor left. Since I is up, the magnetic force can't be up or down. It was either going to be into or out of the page, and we found it is into the page. When a magnetic field has a wire in it, the magnetic force occurs whenever the current and field is perpendicular. If you have I and B in the same direction or opposite direction, it doesn't work. The rule is current, field, and force must be perpendicular to each other. They're called mutually perpendicular. So if current and field are not perpendicular, you get no force. So let's talk proportions. The force depends on the current, the length of the wire, and the field. If I double the current, that would double the force. So I know it's either going to be choice 2 or choice 4. It's going to double the force. And if you switch the direction of current, that will change the direction of force. So I said 2. And just to double check here, let's say that I have my fingers pointing to the right, but now the current is going down. The force would now be going out of the page, and so it would switch direction. Finally, some math in this unit. All right, this is a railgun here. We've got a round metal rod dropped onto 2 metal rails. We have the mass, and notice the mass we would want to change that to kilograms, so that's 0.2. We've got the resistance, of this rod. We have the magnetic field, the length of the rail, that's from here to here, and the battery's voltage. So first we need the direction of conventional current. We know it goes from positive to negative. So in the rod, the current is going up. That's where we're mostly concerned with. So check, labeled I. To calculate the magnitude of current, there's a bunch of choices that have current in it, but since I know the voltage and resistance, I'm just gonna use Ohm's law, guys. That's 13 volts over 6.5 ohms, or 2 amps. Next, we have a force. So I'm going to draw the direction of force using this right-hand rule. I see the field is into the page, so these little X's, you can imagine those are my field. Nothing can be into or out of the page because B is already in that direction. Nothing can be up or down because current is already in that direction. The force must either be left or right. Now, applying the right-hand rule, I'm going to put my thumb up, so in the I direction this way. Fingers point at the page. So the force, the direction my palm is pointing, is left. Well, that's kind of funny. We don't really want that. That means the force is firing the rail back towards the power supply. Well, to switch it, I could either reverse the direction of current, reverse the direction of battery, because that would reverse the direction of current, or reverse the magnetic field. That would cause the force to switch direction. How do I calculate the force, you say? Well, thanks for asking. The force is ILB. So I'm going to take the current that I already calculated was 2. L is 0.4 meters. And B is 0.5 Tesla. And since this is, 2 cancels the 0.5, that is 0.4 newtons left. So I did that, got the force. Bonus here, calculate the acceleration. Acceleration is caused by a force acting on a mass. And since there are no other forces in the x direction, that net force is the only force that's there. So my 0.4 newtons to the left is the only force acting on the 0.2 kilogram mass. And that gets me something like, is it 2 newtons or 2 meters per second? Something along those lines. Let's calculate it just so I don't give you the wrong thing. Yes, 2 meters per second squared, also left. Your object accelerates in the direction of force. So remember, this equation you should be able to calculate. It says, describe the magnetic force being directly proportional to current, length, and field. Determine the direction of magnetic force on a current carrying wire. When that force acts, it is going to have, down here, a force on a current carrying wire is the basis of an electrical motor. Notice that this object started at rest, had a force on it, which caused acceleration. The electricity creates kinetic energy. That must be a motor. Oh, this page. So number 6, electromagnetic induction. Induction is when you have some sort of changing magnetic flux that creates a voltage in nearby conductors. So if I move a magnet, that changes the flux through the wire. The electrical energy comes from the kinetic energy used to move the magnet. So let's say you're out here holding this magnet, your kinetic energy creates the electricity. Oh, that's kind of cool. It means the sandwich that powered my kinetic energy created electricity. Electricity from sandwich. Now, let's say we've got The magnet pulled quickly left. It creates a current. If the magnet is moved more slowly, that would mean less voltage. So if speed goes down, voltage decreases. And you move it in the opposite direction, that would also switch the direction. So I would expect less current because less voltage, and in the opposite direction. With C, I know this looks like a handful, but we're just circling things here, right? When the North Pole slowly moves towards the coil, it induces a small positive current. If you move it faster, I would expect more current in the same direction. Sure. I want to circle 2 things per line here. I know it looks overwhelming. So it says circle 1 choice for current, like its magnitude, and 1 choice for direction. So, one more time. The North Pole moves slowly, inducing a small positive current. If I move it away from the magnet, then I should have less current. And in the opposite direction. Because I switched the direction of velocity, I switched the direction of voltage. Because it says there's less speed at a slower rate, I switched the amount of voltage. If it's stationary, you get nothing. No kinetic energy in, no electricity out. Conservation of energy. Now, if I do the same thing, but I replace it with the South Pole, you get the same current, but the opposite direction. Whenever you make a directional change, like I changed north to south, that changes the direction of voltage. Okay, so now I take my South Pole, it moves away at a faster speed. Faster speed means more current. But notice it has 2 directional changes here. And I'll try to highlight them because I know it's a lot of text together. So it's the South Pole, so that's 1 directional change, moves away from the coil. That's kind of like a double negative here. A North Pole moving towards is the same as a South Pole moving away. Since you made 2 directional changes, that's actually in the same direction. You'd still get a positive voltage. Now, the coil moves towards a stationary magnet. So now the coil is staying still. Sorry, the magnet is staying still and the coil is moving. That'll still give you the same amount of kinetic energy because the kinetic energy of the coil moving is what's now causing this changing flux and creating the voltage. So it's the same speed and still moving towards. So same speed, same current, same direction. If you want the biggest possible voltage, you want to increase the number of coils, the magnetic field, the length of the wire, and the speed. You could also, using the other equation, you could also talk about how the flux includes the change in area. You could say you would want it to take less time. Since flux is the change in area, you could have more area coils. So there's lots of choices here. So you could say more coils, bigger coils, more length, more field, more speed, less time. All of those would increase the voltage. If we were talking about increasing current, you could also lower the resistance, and that would do the same thing. Now, there's a lot with induction. Induction is the only one of these that gets 2 pages. It's so special. It gets 2 pages because you should be able to know all those direction changes and the calculations. So, determine the magnetic flux in the loop when the loop is not in the magnetic field. If the loop is over here, then the flux is 0. remember, flux is flux is how much field goes through that area. So over here where the field is 0, the flux is 0. The unit is Webers. When it's completely in the magnetic field, I'm going to do the same thing, BA, except now, let's say it's right here, 100% of the area is filled with field. So I would take my 5 Tesla field times the area of that rectangle, so 0.2 times 0.2. Sorry, I'm tired. It's a long day. That gets me 0.2 Webers. Now, when you get to induced voltage, I have a choice between 2 equations. And I'm going to show you both. So I'm going to do the more difficult way first. Way number 1, use the original equation. That's N, change in flux over time. I say this is more difficult because I didn't give you a time, but I did give you a speed. How to figure out the time it takes to enter this field is knowing that speed is distance over time. So with a speed of 5 meters per second and a distance of 0.2 meters, the time would be whatever 0.2 divided by 5 is. .04 seconds. There we go. Now, unless it says otherwise, this says nothing about how many coils there are. Assume it's 1 coil. So this would be 1 is N. The final flux is 0.2. The initial flux is 0. And that all occurred in 0.4 seconds. .4 seconds. That gives me a voltage of 5 volts. Hey, do you want to see the other way to do it? The other way to do it, the shortcut equation, because this is entering the field, I can totally use this equation, is NBLV. There's 1 coil, it's a field of 5, it's a length of 0.2, it's a speed of 5. All of those things cancel out to give me a voltage of 5 volts. Both ways work. This way is faster. You can't always use it, but I can use it in this scenario because the loop is entering the field. When it's entering the field, the flux is increasing. And whenever the flux changes, that's when you get a voltage. You don't always get a voltage, you don't always get a current, but since this is a closed loop wire, you do. I can calculate the current because I have a voltage and resistance. Right? So that I say it correctly, you always have a voltage, that's 5 volts. You don't always have a current. To have the current, you need that closed loop. So 5/4 or 1.25 amps. If I put 5 loops in place of just 1, well, this NBLV equation means that if I have 5 loops and each loop gets 5 volts each, my new voltage would be 5 times more than the original. I'd have 25 volts. Nice how that works out. Once it's fully inside the field and continues to move, so let's say it is this picture, and then some moments later it's here. There's a problem. From here to here, between these 2 pictures, there is no change in flux. B stays the same. The area enclosed stays the same. So here's where the shortcoming of this equation is. You can only use this equation if you are entering the field or exiting the field. You cannot use this equation if the loop is just moving through the middle of the field. If the loop's just moving through the middle of the field, then the flux doesn't change. You have to use this other guy, the Faraday's law full equation, using the n change in flux over time, because between these two pictures, the flux doesn't change. Between these two pictures, the flux in the black rectangle is 0.2. The flux in the green rectangle is also 0.2. And when I do that out, it doesn't super matter. The voltage is 0. The voltage is 0 when you're not entering or exiting the field. That's why when all 4 loops are moving through the field, just like this one, B and D are going to have a voltage, right? B and D have a voltage. C does not have a voltage. It's not entering or exiting the field, so C is going to be over here at the least. A actually gets the most voltage because of this little thing in the equation. When we talk about the L in the BLV equation, the L it's talking about is the L that's perpendicular to the direction of motion. So A has a longer value for L than the other ones. A has a longer value of L, so A has more voltage. So A has the most, then B equals D for the amount of voltage induced or created in these coils. Ooh, but just for a fun fact, B and D have the same voltage, but their currents are in opposite directions. D's current goes clockwise, B's current goes counterclockwise in a right-hand rule that you don't need to know for 5470. But you should know that B and D, because they have opposite changes in flux, will have opposite directions of current. So that was a lot before we double-checked this. For induction, you should know that a moving magnetic field or a changing magnetic flux creates a voltage. Back in the day, they used to call this an electromotive force, but I hate that word because it's not a force. It's literally a voltage. It's measured in volts. They used to call it an electromagnetic force, thinking like it's a separate force from magnetism, right? But it's not. It's just a regular voltage, just the way a lemon battery makes a voltage, right? It doesn't need a special name. Whenever you have a changing magnetic flux, that produces, hey, electric potential, that's another word for voltage. And as long as there's a closed loop, you get a current. Now, how does that make a generator? Well, a generator, right? A generator is something that takes kinetic energy, so your kinetic energy that you put in to move this coil, and turns it into electricity, turns it into current. So that's changing your kinetic energy to electricity. This one, be able to do all the calculations here, right? So it says determine the strength of the induced electric potential. Oh, we're just using all the synonyms for voltage here. You should know that the voltage in the conductor is proportional to number of coils, the speed, the length, the amount of field. This standard is just putting in words that thing. You can do this. Which, believe it or not, leaves our very last page. Be able to tell apart motors and generators. If it converts kinetic energy into electricity, that is called a generator. If it takes electricity and moves, creates kinetic energy, it's a motor. And if you have trouble telling these apart, a motor creates motion. A generator can power your house with electricity. Which of the following is not an example of a power plant that uses a generator? A fuel cell, right? All of the other ones I talk about in class. A hydroelectric power plant has that like water wheel that turns. The water wheel's kinetic energy turns into electricity. That's supposed to be a light bulb. You got it? Nuclear does the same thing, but instead of water falling down through the turbine, it's very hot steam going up through the turbine. Same with natural gas. They use natural gas to heat water. It makes steam. Steam turns the turbine. Electricity comes out. Bam. Now, a motor uses the magnetic force on a current carrying wire. We had just done it with this page. A motor takes electricity to make kinetic energy, and it comes from this magnetic force. That's why the railgun starts to move. Whereas a generator is caused by electromagnetic induction. Just so you can tell them apart, an electromagnetic induction is when you have a changing magnetic flux to create an electric field. It's the opposite of electromagnetism, which takes electricity to create a magnetic field. In reality, both the electric and magnetic forces are the same force. They just look slightly different. Deep down, mathematically, this one force, the electromagnetic force, controls so many different things. Besides electricity and magnetism, it controls all of chemistry too. All right, everyone, that is enough sidetracking. We are done for the day. Good luck on your test, either Friday or Monday or Tuesday, on whatever day you're taking this test. Best of luck.